Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 58, we continue with the GIS theme, and the title of this lecture is Geospatial Analysis, and this is part 1 of this lecture. So, the different concepts that we will cover will be on geospatial analysis in general. Then we will look into ordinary least squares regression in the context of GIS. Then something called geographically weighted regression, which is very specific to GIS. And we will also look into forest-based classification and regression in the GIS. So, GIS software has advanced quite a lot in the recent years, and now we can do a lot of different kinds of analysis using GIS softwares. It's not only representing spatial features like polygons, points, and attaching data to it. Now, using that data or adding further data to it, like we have shown you earlier in our previous lecture, that with joins we can add more data to it. So now we can do much more analysis with that. Now different kinds of analysis could be done. 2D analysis mostly, which deals with spatial data. 3D analysis, where it looks into both the 2D features as well as the height of the buildings and so on. So we can do a lot of 3D models as well, or 3D visualizations as well. And then we can also do 4D analysis or temporal analysis. That is, we can store data over different periods of time, and that also could be visualized and represented spatially. So the different analysis that you can do would be, there are various kinds of analysis. ArcGIS Pro, for example, provides more than 1500 plus tools of different, that means you have tools for data management, data conversion, data analysis, and it also provides us various kinds of wizards. That means it's a step-by-step process in which you can achieve or do something, right? That which guides, the software guides you to do those things. So with those things, we can do different kinds of analysis, such as proximity or overlay analysis. This is a typical analysis required in urban planning. Then network analysis, where we can find shortest path, or we can solve the traveling salesman problem, those kind of analysis. Then statistical analysis or geostatistical analysis, you can say, and then temporal analysis and so on. Now we can do a lot of 3D visualization of data. We can build a lot of models through model builder, and we can do a lot of prediction using the models that we build. And then we can also do a lot of automation. For example, we can do a lot of use Python to automate certain analysis steps, and also we can use extension, and we use ArcGIS extensions and then integrate into Python programs as well. So this gives us a lot of flexibility to use this tools or this analysis modules in other programs that we build, or we can use Python programs inside ArcGIS as well. So we are talking about ArcGIS, but there are several softwares in the market, as well as there are a lot of open source softwares as well. Now the reason we are talking with ArcGIS, because it is one of the most common professionally used software, and the tools over here, more or less similar kinds of tools would be also available in other softwares as well, but of course the comments and all would be a little bit different. So today we will discuss about the spatial statistics toolbox, where we will look into, actually we will start into the different geospatial analysis that could be done. And for example, we can do pattern analysis, we can do cluster analysis, we can do GLR and GWR. This is this is generalized linear regression, and then geographically weighted regression. So all these things we can do. Then random forest, local bivariate, measuring geographic distributions, all these things we can do. So when you click on analysis, then on tools, then this box opens and you can see the different options that are there: analyzing patterns, assessing sensitivity, mapping clusters, measuring geographic distributions, modeling spatial relationships, and spatial component utilities, and so on. Like Moran's eigenvector, all these things also could be computed. So in the images you can see this is somewhere an example of hotspot analysis that's being conducted, then cluster and outlier analysis, then the different regressions over here, then local bivariate analysis, and so on. So all this we have learned when we have learned machine learning. We have learned all these different mathematical, we have explored the mathematics as well as the actual Python solutions for this kind of problems, and now we are also seeing how this could be done in Python as in GIS as well. So first we will start with ordinary least square regression, or otherwise known as OLS regression. So for this one thing that we can do more over here is we can always conduct this analysis in using data from Excel or CSV files, then using either Python or SPSS or any kind of statistical software. But over here, if I do it via GIS, then it's not only we can use a lot of spatial, we can see we can extract some data from those different spatial features from the GIS maps and all. In addition to that, what we can do is that means ArcGIS can also evaluate the spatial distribution of residual errors. That means when we are predicting or using, if we have the data in front, we have first trained the model, or we have determined the model coefficients, and then we are predicting with that. We can also show the errors and how much is the error, that also could be showed in the map. So first what we have to do is we have to prepare the data. That means data is joined to a feature class first, that is either a shapefile or a file geodatabase. This is a special kind of file where it's like a database, several different layers could be put together, and or it could be a single shapefile as well. So we can use any of this data, and then we can take that particular that shapefile or that particular group of data, and then we can extract the features that we require, and then once we are ready with that data, then we can start the regression. So the fields for analysis are formatted as numeric and not text in this particular case, because GIS, ArcGIS particularly cannot handle text data. We have to convert it into numeric data. For example, when we already learned about dummy coding earlier. That means we can convert into 0 and 1 the thing that the encoders were doing. We have to first do it ourselves manually and then put that in the database. So directly we cannot use text. We have to convert all data to numeric, and then we can run the models and all. So OLS either failed or skip records with missing values. So we should ensure that there are no missing values, but if they are there, then there may be some errors, or it may skip those particular records. Now first we have to go to ArcGIS Pro, and then we have to click on the analysis tab, and then within the analysis tab we have to click on tools, which will open the geoprocessing pane, and within that we have to select this ordinary least square, which is one of the spatial statistic tools. Now within that ordinary least square tool, there are several fields that we have to fill up. The first field is of course input feature class, which actually tells us that which layer that we have to open, that the layer containing the geographic area or areas that is or are selected. So that has to be first chosen. That means the layer in which we would be working. And then we have to select one unique ID field, that is almost like the primary key thing, but in each GIS table for each feature there is a unique ID. We can use that as well. So we can select the field with a unique value for every row, and then output feature class has to be selected to choose a name for the new layer that will contain the results and the residuals. So once the regression runs, then the results of that regression, the predicted values would be stored, right? So that will be stored in a new file or a new layer, right? So that's what we have to specify, what would be the name of that new layer, and then we have to choose the dependent variables and the explanatory variables. So the dependent variables is the variable that we need to predict, and the explanatory variables are the different independent variables which actually will help us in predicting the dependent variable. And once we have done with it, then we click on run. Now how does it look? This is the interface that over here you can see when you click on analysis, then this window for this opens up, and then you have to click on tools. When you click on tools, then all the statistical, you get the options, and then you have to go to geoprocessing, and then within that you have to select ordinary least squares, and when you get that you will see that these are the different fields that we have to fill up. Now over here you can see the first field is the input feature class. What we have done is we have used the data sets which are available from ESRI, which is the parent software company of ArcGIS. So whatever is there in the help files or the different data sets, we have used that to generate this particular presentation. So, the New York State project, that is the input feature class, and unique ID field name is given, and then the output feature class is given, that is New York State project underscore ordinary least squares, that we have given over here. And then what we are predicting is the median home value, that is we are trying to predict the price of residential buildings, right? And what are the explanatory variables? Based on the data that is available in that layer, we have data on the land area, the total housing units, vacancy rate, owner occupied housing units, renter occupied housing units, home ownership rate, median contact rate, and so on, right? And median home value and so on. So what we have to now, same as the process of modeling which we have followed earlier, you have to choose, or you have to frame your hypothesis to understand which are the variables which are having a role on the overall median value, or which actually have an influence. For example, the vacancy rate is a big deal, right? That means if there is more vacancy, the rates fall down, right? So all this will come into play, and we will run the model, and once we run the model, we see what we get. The result is this one, where we see that this is the output, that means the shapefile that we just created. So we are the data for that shapefile is being shown over here, and what you are seeing over here is all the different counties that has been, for which the data we are running the regression, the median value, home value of those particular counties and all. So in that case, we are seeing this different colors of shade, right? This actually indicates the standard deviation, or what is the variance of that particular this residuals that we are predicting, right? So if it is within 2.5 standard deviation, minus 2.5, it is dark blue. If it is greater than 2.5 standard, it is dark red, and average ones are blue, which is mostly, you can see blue. So that means more or less we are predicting pretty okay, and we can also map the ones which are not being predicted properly, right? So that means we have to investigate further that why it is not predicting properly and so on. So this actually is a map of the residuals. So then this is how the data is coming after prediction. But of course we need to, because we are running the model, we can apply this model in some other geographical area, or if some counties do not have the value or the result, then we can use this model to predict for theirs. But we first need to understand the different results of the model that we have run, or the statistics of that particular fit of this linear regression, right? So over here you can see this is the intercept, this is the beta 0 value, and then these are the different variables which are actually having a effect or on the median home income, home price. So we see the first value is total number of housing units, then the second one is vacancy rate, then the home ownership rate, and then the contract rent, and so on. So we can see that where the home ownership rate is more, that median value is actually lower, right? So these are the things that we can see, and we can see the probability values that we are getting, which actually, if it is within 0.005, then it is 95% within confidence interval, so that we can check also. And one thing I just missed, the vacancy rate, which this indicates if it is high, then the median value is high. So probably here the problem here, what we are trying to, I said earlier that if vacancy rate is high, then that means median value would be lower, right? But over here we are seeing that if vacancy rate is high, the median value would be high. The reason may be that because it is very high, or rather the vacancy rate is also, nobody can afford that much, right? So that's why more number of housing units are vacant. So that is usually, it's not shouldn't be the case, but this means it is a case of oversupply, right? So then what we are saying is we are also checking the VIF values and so on, and we already understand what is VIF for. It is variance inflation factor. So if this is within the value of 7.5, then there is no serious multicollinearity also, so we can accept this particular regression. So now to summarize the statistics, so these are the different coefficients and the variables that are selected for the model. But now we are trying to understand the statistics where we find the R squared value comes to around 0.923328, which is pretty good, and the adjusted R squared is a little bit less but still 0.9, and so mostly that means about 92.3% of the variation in county median home value is explained by this predictors, right? So it's a very good model, I will say, but we have to check that if it is overfitting or not also. So, but along with this, we are looking into F statistics, which is also within the probability is within 0.005. That means it's a good model fit, and we are also getting some more statistics, Wald statistics, then Cuenca BP statistic, and then Jark-Bera statistic. So out of this, these two new statistics that we are coming out with, that is this Cuenca BP statistic, this actually talks about spatial heterogeneity. So if this particular value is, this actually indicates that since Cuenca BP test statistic was significant, we may consider that OLS is not good enough for this particular model, but probably a better would be to create a geographically weighted regression. That means there are a lot of housing submarkets that we have to consider, right? That means housing, it is not uniform everywhere, the housing price, it varies as per different locales or localities, right? So that's, this statistic actually tells us that there is a lot of spatial heterogeneity as well. And then the Jark-Bera statistic, it talks about residual errors are not normally distributed. So that is another thing, that sometimes we do assumption that the residuals are normally distributed, but here we are saying it is not. So that is another indicator that we have different distributions that has to be considered. So that basically means it is better to go for separate regressions of different zones, right? And one way to do that is via geographically weighted regression. That means instead of finding one common equation, we find different equations for different areas. Now different areas, it could be for each individual for each individual county, we would be able to predict the exact value, and how we can do that is we would frame a regression equation for that county separately, right? Now this GWR is basically, why we are doing GWR is basically we should have to look into Tobler's first law of geography. What it states is that everything is related to everything else, but near things are more related than distant things. So what Tobler's first law of geography states that near things have got more influence on what is on my characteristics, right? So global models may sometimes fail to account for local spatial variations, and that is why we have to have an alternative way to also conduct regressions. So GWR is a local regression model, and what we can do is we can develop the model in such a way so that coefficients can vary across this different space. That means we are not using the same uniform coefficient across everywhere, right? So the model structure would be same, the variables may be same, but the coefficients would vary in the different locations. So what we do is separate equations are found by incorporating the dependent and the explanatory variables of features within the neighborhood of each target feature. That means whenever we are developing the regression equation, we are only considering the nearby or neighborhoods or locations which are at certain proximity. We are not considering locations which are very far away, right? But as you can understand that this actually requires us to have a very big data set. That means with small data set, we cannot conduct GWR. That means if we have got many locations and many samples, that means for each sample, when I am doing a regression, I will take the nearby neighborhoods or the nearby counties, and then I will develop a regression model. So as we understand, for each regression model there has to be a significant number of samples that has to be conducted, and that means we require a huge amount of data because we are creating so many separate regression equations. So everything remains same now that we have chosen geographically weighted regression. The only thing that gets added to this is the model type. You see there we have taken continuous Gaussian, so we are choosing the model type, and we are also choosing the number of something new has come, number of neighbors, and then the neighborhood selection method, right? And then within that minimum number of neighbors and maximum number of neighbors could be also given. Now what we are doing over here is, first of all, when we are doing geographically weighted regression, it could be of different kinds of regression. It could be a continuous Gaussian regression, means Gaussian means the normal distribution, right? So for continuous, we are considering continuous dependent variables in this particular case. If we are trying to predict the value of a continuous dependent variable, then a continuous variable, then we are going to use the the linear method, right? So this we are going for continuous Gaussian. Then if we are trying to predict for zeros and ones, that is yes or no, it's a binary outcome, right? So we are going to use the binary logistic regression equation. So for binary dependent variables 1 or 0, we would be selecting binary logistic instead of continuous Gaussian. And then if we have got discrete non-negative count data, that is like number of crime incidents in a particular zone or disease cases in a particular zone, we can also choose count which follows Poisson distribution, and that one also we could be used for what kind of model we are trying to develop. Now the number of neighbors, actually we first need to understand, because we are doing geographically weighted regression, that means how much nearby locations we should consider, right? So that is where the shape and the extent of the neighborhood parameters become very important. Now the shape and the extent most likely refers to either we can take the number of neighbors, or we can take a distance band. That means within a distance band, we can give within this particular distance band whatever is the number of neighbors that we will choose. Otherwise we give a number of neighbors, but we are not giving the distance band. So in that case it is kind of adaptive. That means the values may change, and the distance will vary, and the data sets will have particularly data sets with varying density, there we may have some issues also, right? So that means either we can fix the number of neighbors, or we can fix the distance band where the distance becomes fixed, and this is usually for uniformly distributed data, whereas for data sets with varying density, we may go for this number of neighbors, but also depending on the nature of the density, we may have some trouble with this also as well. So these are the first two things that we have to select, right? And then comes the neighborhood selection method, where we can select something called golden search, or we can use something called manual intervals, or usual different intervals, right? So this golden search basically means automatically the algorithm finds the optimal bandwidth, that is the distance or neighbor count, whichever is selected by in the previous step, by minimizing the corrected Akai information criterion. So we have already done this earlier. So this AICC criteria, this is looked into, and we find that whichever shows the lesser amount of AICC, which distance band and which is resulting in lesser value, we will choose that as the best solution, right? And manual intervals allows defining a range of neighborhood sizes, minimum, maximum, and we can also give this usually we go for minimizing AICC. That means within this band, whatever value minimizes AICC, that we have to choose. And then it could be also user defined, where specifies the exact fixed number of neighbors in this particular case. Sorry for the overlapping of the text over here. And then finally, once the model is run, after giving all this criteria, this one actually is automating the process of selecting the right combination or the distance band or the right number of neighbors and all. And once we do that, we get similar results that we got earlier for the OLS regression as well, where we can plot the residuals for each one of these particular counties, right? Now the first set of a figure over here, this is the golden search result, which actually tells us that for different number of neighbors, the value of AICC was tested, and it was found that these are the values, which is not too much different. So something around, I think 31 or 84 or 30, some of them must be the best result, giving the best result, right? So if the neighbor count is 30 or 31, probably the model would work best. Now for each explanatory variable xi, GWR would produce a spatial map of coefficients. That means for every variable xi, we will get, that means one set of coefficients, and that would be different for different cases of I, right? And each spatial unit shows a coefficient value. So that's the case. That means we get many regression equations, and the maximum number of neighboring features that is accepted is around 1000, and this would be the closest 1000. So we cannot go beyond that. Like over here, we have found that only 30 is good enough, right? But we can go till 100. That's the maximum value, and it is suitable for data sets with only with several hundred features, and do not work with multi-point data such as city bus stop, utility poles, or leader data, and so on. Now, the model diagnostic has been done, and you can see that again that the model parameters, the dependent variable and the explanatory variables, more or less those are similar what we have got earlier, and the number of neighbors have been chosen is 31, and R square value is 0.9407, adjusted R square is 0.9314, which is a slight improvement from the normal OLS regression, right? And AIC value is given, and more or less this shows that a geographically weighted regression is probably giving better predictions compared to the OLS regression. And in addition, we can also visualize the different the variables, or the relationship between the variables, as well as the relationship between the residuals after running the geographically weighted regression. So this one actually shows the standardized residual plot, and you can see the distribution of the standardized residual. Now, standardized residual is residual divided by standard error, right? And if the value is within -2 to +2, it is all fine. It is acceptable prediction, but if it is greater than +2 or lesser than -2, then there is either strong underestimation or overestimation. So we have to be careful about that, right? So this one we can check, and along with that we have plotted here the standardized residual and the predicted plot. So you can see that it should be somewhere in the middle, but we are seeing some values like this which we have to be concerned about, right? So these are beyond the standard residual. So it is beyond that value of 2 standard deviation or more, right? And then here we can see the relationship between each of these particular variables, that is median home versus median home obviously will be a straight line, whereas from the others we can see the relationship how they vary between total housing unit and median this one. So these two variables, vacancy rate versus total housing. So all these things we can also test using from these results. We can check from this result. Then we come to forest-based classification and regression. So over here we have applied one of the machine learning techniques that we learned in our earlier lecture in the GIS context, and two supervised machine learning methods. One is random forest algorithm and the extreme gradient boosting or XGBoost. Both can be applied, and this could be used for building models and for also doing predictions, right, for new areas or for different time periods or so on. So it can handle both categorical variables, which was not possible in OLS earlier, and also continuous variables. So it can do both regression as well as classification. And explanatory variables could be fields in the attribute table of the training features, or it could be raster data sets or distance features used to calculate proximity values for use as an additional variables. So distance we are calculating from the GIS map itself, from the GIS from the software itself, that how far away it is from something else. Then raster data sets, if we have got land use map or some vegetation, some images, so those could be, we can extract data from that, or we can straight away take the data that's there in the table itself, right? So the model could be trained only. That means we just train the model and we see the importance of the features and so on. So that could be the model. So we assess the model performance, or it could be predict to features also. That means we can predict missing values or values in different study area or time period, or it could be predict to rasters as well. That means in case all explanatory variables are raster, then the prediction can be also a raster surface. So obviously when we are predicting, we have to create a new feature and we will store that data in that. So we can determine the variable importance, and in case of ArcGIS Pro, the forest-based classification tool, the regression tool, utilizes around 66% of training data for model building and 33% of data, which is otherwise known as out-of-bag data, for validation. So that is the standard procedure in which ArcGIS Pro runs a random forest or this decision tree regression tool, right? Now so diagnostics are of different kind. We look into the out of bag errors. That means when we are predicting for the out of bag data, what kind of results, what kind of errors we are getting, residuals we are getting. Then we look into the, which we already in earlier in the OLS also we are getting those values. Then we can get the mean squared error for regression, and also for classification we can get accuracy values and so on. So we can further validate the model by taking training data as 90%, that out of the entire data we can separately keep 10% data for doing future predictions, right. So this is in addition to this out of bag data for validation, right. So this 66% and 33% will be conducted with this 90% data. Then confusion metrics could be developed for sensitivity and accuracy. This we can get from the results of the regression as well. So over here you see a case study. This case study I got from a old presentation from ESRI. I'm not exactly sure, but this is a very interesting case. So we are using that. So I am not sure about the exact source because it was a long time ago, but we can always add that if somebody tells us if they find this particular image. This data set is from Uganda, and the surrounding East African region like Lake Victoria, Kampala, Rwanda, Burundi and Tanzania. And what we are trying to do over here, we are trying to predict the incidence of dengue, right. And that prediction is based on several features. Some of them are data attributes, some of them are raster features, some of them are proximity features and so on. And here we are running a random forest decision tree to model the incidence that area will have dengue or not, and we are also running a train only model initially, right. So over here you can see that this spots tells us the cases or locations where dengue is detected, the red spots and the black spots. So this is where we are tested, and we found that the red spots are the location where we found dengue. So we are trying to now find which features are contributing to this outbreak of dengue, right. And for that we have got different sorts of features over here. Now looking into the features, this is the big list of features that has been utilized in this particular model. And these are all biovariables that you can see over here. These are standardized climate indicators derived from global climatic data sets such as WorldClim, whereas the other data set is, we have already listed what data set it is from, right. So for example, the first one is Euclidean distance from hotels or tourism facilities. Next one is distance from each location to the nearest river from that particular location. So these are all proximity values, right. Then distance to the nearest lake or major water body. Then we are using this land cover classification data set for vegetation and land use type. Then raster data set representing spatial distribution of population density. Then population distribution data set representing human settlement density. Then elevation of that particular area, the mean diurnal temperature range, temperature seasonality, indicating variation of temperature, maximum temperature of the warmest month, minimum temperature of the coldest month, precipitation during wettest month, precipitation during the driest month. All this data we are putting in, and we are seeing that there is a some relation between the incidence of dengue and all these different features. So when we run the model, of course this red indicates dengue incidence and black indicates there is no cases of dengue from the data that we have got. And we run the model with total number of trees is 100, because as you know, when we are doing a random forest model, we have to specify how many trees we want to build, and the data for tree, that means 100% of the data will be utilized for building each of these trees. And that means you can do some amount of pick and choose. That means that means you can you may not need to we can also specify that what proportion of the data set could be going we can use for building each tree, and it can randomly choose those particular data. And then validation speed is 10%, that means we keep 10% data for validation for future. So this is once we run the results, we get these results. You can see the variable importance over here. We already have taught you how to calculate for decision trees, how to calculate the importance of each variable, and we have already discussed that earlier, so I am not going to repeat that. So you can see over here the values of each of these features that actually tells us that which are important, and then you can see the sensitivity and the accuracy scores for the predictions, for the training data, and then for the validation data. So this data is more important. Of course, training data would be one because it is perfectly predicting, but for actual accuracy testing, we need to see what is the prediction for the validation data set, and we see around 86% accuracy. So which is pretty good prediction, I would say. So what we see from this importance criteria is human activity and population density are strong predictors. Climate variables strongly affect mosquito distribution, and elevation influences temperature and habitat suitability. And so these are some of the findings that comes from this decision tree, and the model performs very well on the training data. Validation accuracies are around 86%, which is also indicates strong predictive accuracy. So these are some of the references that I have used. To conclude, geospatial analytical methods such as OLS, GWR, and forest-based machine learning models enable spatial datasets to reveal relationships, local variations, and predictive patterns that supports evidence-based urban and environmental decision making. Thank you.